된 건가? Okay. Okay, we'll start our session 4, which is going to be sequences and limits. Okay, so basically, we started learning about basic real number system, and now we're going to see what we can do with this real number system. So there are a lot of ways to start, but in this class, I decided to start with a sequence. This is because of a few reasons. Firstly, as I wrote it on a slide, it's very important to know about functions. So knowing about functions, I think it's like, at least in analysis or economic term, in the end, you have to know about functions and like how functions operates. And that's our like main goal, I think, for analysis in economic research sense. And if you want to get used to the function, it's better if we start with sequences first. Why, you might ask? And this is because sequences are a special kind of functions, which I'll later explain. But for now, just note that sequence is actually just some special form of function that you're using. So like function is a more general term, and sequence is just like a special type of function. So just remember that. And we will come back to this later in the end of the session, or maybe next session. So, and also, sequence is like a good way, like it's a good starting point to know about limits, because I feel like sequence is very intuitive because it has like some notion of moving force. So for example, like if you have some functions, sequences, it kind of feels like the sequence is like moving from A1 to 4, right? Going onward. So this like sort of motion is actually I think it's very intuitive when you first start to understand limits. So it's very interesting to also learn about basic qualities of limits using sequences. But note in mind that limits is not limited to sequences. So later you'll see that you can have a functional limit, like limit of a function, limit of a sequence, limit of sometimes even sets, I think. I'm not sure, but there's like various subjects you can use to operate limits. So, but we're just starting from sequence to get more familiar with the overall concept of limits. And also sequence is also itself a very important concept. All right. So we have a goal again. So we'll be learning about, well, basically sequences and limits. So that's it. So we'll be learning about how sequences work and what it means and how we can define limits on a sequence. It might be a bit complicated for people who haven't taken courses like undergraduate analysis courses where you don't define rigorous definition of limit. So just bear with me so that I'll try to explain things as we go. Okay, so we'll start with the definition of a sequence. But before we start, let me write you the attendance code for people who are listening to the videos. So the attendance code is 55. So 55, I'm not sure if you can see it. So it's 55. So students who are taking the videos, you can send me this attendance code through email. Okay, so we go with the definition of a sequence. So sequence is basically an enumerated collection of objects. So what does this mean? It's just what it is. I wrote in the slide. I also gave you an example right before. It's just like some enumeration of like collection of objects with some index in it. So like A1, A2, A3. Like as I said, like a sort of objects that seem to have some sort of sequence, like some sort of orders, like A1, A2, A3, like that. We call that sequences, and usually each collection denotes some values. And for convenience, we're just gonna say that it denotes like real numbers throughout our lecture. But note that sequences can also be like a set. So like for now, we're just gonna think like A1, A2 is like some real number, like this. But sometimes, like if you in a more general sense, sequence can be a set, so like maybe something like this. So It really depends on what you use. Like the value can be kind of anything. So just note that. But for now, we're just gonna assume that it has like a real value, real number value, just for convenience. Okay, so for example, we can have a sequence where A1 is 1, A2 is 2, A3 is 3, etc. And it goes on. And so instead of writing it all down, which is very inconvenient, and we can't do it for all the sequences if the sequence is infinite. And by the way, the sequence can be finite as well. So like there could be like finite sequences. So like the sequence can end at like A5. So that's also sequence. But still, most of the sequences we define are usually sequences where it goes on forever, from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to infinity. So it's impossible to like write down all the values for sequences. So instead of defining it by one, what we would usually do is like write it into some notation like what I wrote in the slide. So basically we kind of use some sort of recursive notations where like an is 1 over n like this. So it's more easier to see this because then you can kind of see how this is going to go. Like A1 is 1, A1 is 1 over 2, A3 is 1 over 3, etc. By using this, we can like kind of describe the whole set without having to write it every time you just write your sequences. I hope you're already familiar with this because you use sequence a lot already in like undergraduate calculus courses, so you shouldn't be like too familiar with these concepts of sequence. And this is where we start. So, okay, we understand that that's the definition of a sequence. Then we talk about like bit of motivation again is why do we learn sequences? Well, as I said formally, there are many benefits from actually knowing about sequences. Like as I said, there are a lot of properties the sequence has, but for now we'll focus on limits. So basically, at least this is like my opinion, so don't take it too generally. Sequence, I think, is a good starting point to get used to the concept of limit. So as I said, in example, consider like the sequence where an is 1 over n. So where does this tend to as n goes to infinity? Anyone? Where does this go if n goes to infinity? Yeah, 0. So that's very easy, right? An goes to infinity as n goes to infinity. And we kind of use this in properties as we say this tends to 0 as n goes to infinity. In Korean, I think n이 무한대로 갈수록 이제 an이 0으로 간다라고 표현을 하죠. So, from basic calculus, you should know that, well, an goes to 0. It tends to 0, or goes to 0, something like that. But it's a very vague expression. So what does tend to really mean? So what does it mean for an object to go from one place to another? Because you might not be familiar with this, but in math, like in a definition sense, there's no such thing as an object that moves. So like if you're, I'm not sure, I'm not a physics major, but if you're in physics, you deal with a lot of the objects that moves, right? But in a mathematical sense, you have to think of every object as being static. There's no such thing as an object moving to somewhere. So it kind of sounds weird when you say an tends to 0 or an moves to 0, goes to 0, because there's no object that's moving. There's no sense of motion there, although it's very intuitive to understand it that way. So what does this mean? Oh, let me tell you, like, but like some of you might think like, I think an tends to something is very intuitive and it's very rigorous in your opinion. So I'll give you some example where actually you're using it in a very vague way. So this is like one very good example. As we said, we say tend means an goes to 0, but an is not 0 exactly. If you remember like basic calculus courses, you'll talk about like an goes to 0, but n is not exactly 0, something like that. You might remember this. But there's a problem here. So instead of sequences, let's just go for like a functional expression stuff. Let's think about this equation where it's n minus 1 times n plus 1 over n minus 1. And we'll see that we already know that what does it tend to as n goes to 1? It goes to 2, right? You kind of already see this because you already took a lot of calculus courses. You'll see a concept where you just like divide it and just let n goes to 1 and just goes to 2. So it tends to 2. But just remember that as I said, tends to, in calculus definition we say that n goes to 1, but not n the n does not become 1, right? That's like how we define tend. But if you remember undergraduate calculus class, or remember like the proofs you did in those classes, this is basically how we prove it. So we start from n minus 1 times n plus 1 over n minus 1. And you divide n minus 1 on the both sides, because why is this possible? Because we assume that n is not 0, n is not 1, right? If n was 1, then it shouldn't be defined because the denominator is going to be 0, which is not defined in mathematical term. But we can divide it because we assume that n tends to 1 means n is not 1. So we can do this. In the first equation, okay, that makes sense. So like as n is not 1, we can get rid of the n minus 1. But then n plus 1 becomes 2. Why is that? Because n is 1. And this is kind of weird part because we assumed in the first equations that n is now 1. So n does not go to 1. But when we are solving for the n part in the equation 2, the answer becomes 2 because n is 1. So it's like, why are we defining two things? It's very ambiguous to define it because it doesn't make any sense. We just said n is now 1, but then we just say n is 1. And how is the equation 1 even possible? So that's where the problem comes out. So what the heck? Again, we said 10 mean n goes close to 1, but it's not exactly 1, but we just did both of it. So here's the confusion comes up because what are we really doing with the limits? And it's very important because limit is a very crucial concept in mathematics and also economics. So if you don't know the overall process of what is happening, it's very likely that you will get a very weird answer and you think it's right. At least when you're solving very hard questions. I hope some of you might be familiar with this. So we have this problem with the limit. So what we have to do is define it more rigorously. So we're getting a rigorous definition of a limit. So as we saw, that limit had a problem with a sequence. So how are we going to define exactly what it means for an to tend to some element? So this is how we do it. For your reminder, if you are encountering this for the first time, it's very likely that it's very confusing, but that's very normal. So just let it sink in. Just bear with me. So this is how we define limit of a sequence in a very rigorous term. So it's in the box. So we say that a sequence an tends to a or goes to a if for every epsilon there's some natural number n such that an minus a is smaller than epsilon. So what does this mean? So basically this is called some sort of epsilon n method. Some of you might be more familiar with epsilon delta method, which will also come out, but in sequence we say epsilon n method. And if you encounter this for the first time, you'll be very confused by it, and you might not understand the notations. And unfortunately, if you have to prove something in analysis and calculus, this method or something similar will always haunt your life in that class. So just get started to get used to it. So take your time to let it sink in. So what does this mean though? Well, I wrote down some intuitive meaning I think kind of works more better, which is basically what you're doing is for any small positive value epsilon, we can always get the index of the sequence, which is n, big enough to make an close to a. For example, like, let me give you some example. For example, like there's a sequence. Let's just write an XY graph. And that's YA right there. So let's say, what does it mean for an to go to a? It's something like this. So we'll have a sequence where the sequence value will tend to a. So we'll go like, for example, like this. Like this. What you can see, let's assume that this curve is like the values of the sequences. So what you see is that, and let's write, so the x-axis is basically like the index of the sequence. So if you go to the right side, it means that the sequence is going from A1, A2, A3, and 4. So it's moving forward. So what you can see is that as the sequence index becomes larger and larger, it gets closer to A, which is the limit we have. And we say that an's limit is A if for any sort of epsilon. So, for example, so let's say like an epsilon is like an interval. For example, let's say it's like this. So like let's suppose like an epsilon is like a So we write some sort of epsilon which marks like the interval between A. So we have this interval, and you can see that as an becomes larger, the values of the sequence goes inside the sequence. I mean, it goes inside this interval because, for example, here right now an's are not in the sequence, right? But if you get an big enough, same interval, you see that after this part, all the sequences are inside this epsilon interval, right? And because we were saying that it holds for every epsilon, this means that let's make a smaller interval, like this. Smaller, right? But still, even if the epsilon is small, if you get n large enough, maybe like here, then after this point, the an is inside this interval, right? And you can kind of see because an becomes so close to A, this holds for every epsilon intervals, even if epsilon interval was really, really small. As long as you get the value of the n large enough, then every sequences after that will be inside this interval. So this is kind of like the intuition you can think about. And trust me, it's going to take some time if you're first encountering this, understand this concept, but just like kind of remember like, it's kind of like the way where a person give you like interval and you're trying to squeeze the sequences and see at what point after a sequence starts to go inside those interval that is given by someone else. So I kind of gave you like another example in the slide, which is you can kind of think of this process as like two people tossing a ball to each other. So what this means is that there are like two people and one person kind of tosses like some epsilon value to you, and you have to toss some other n value to him to show that in this n value, after this, every sequence is inside the epsilon. And and after you do it, that guy gives you another smaller epsilon, and you kind of toss back another n. It's like a multiple process where like for every epsilon he tosses, you toss every n, some sort of n. So like it's how the overall process of limit goes. Any questions? And it's okay if you don't understand first what this means. If you haven't encountered this, it's going to be a very hard concept. But just like try to get used to what it kind of means, and after it, it's going to be very easy. Let's just leave this one. Oh, and in case you don't know about the notations, like the, I think you already know this, but in the definition, we have this, like this is just absolute value. So we're just like subtracting an and a and getting absolute value, which kind of means like the distance between an and a, right? So that's why we're doing like interval, because a and a kind of means like the distance between a and the sequences. So it's like some sort of an interval that contains a. And we kind of try and see that if the interval contains, you know, the sequences. All right, let's go on. So, in terms of sequences, we can say something has a limit that it converges and something diverges. You already know this probably. So, if a sequence has a finite limit, we say that the sequence converges. So, what does this mean? So, like, remember like the notation where I said an is 1 over n, and some of you guys already told me that n goes to infinity, the value goes to 0, right? And 0 is finite. So what this means is that if the sequence has a limit that is finite, which actually is kind of like a definition of a limit, but still, if it has a finite limit, we say it converges to some element, which is a here. But if sequences goes to infinity, could be positive or negative. For example, think about like the very basic function, I mean sequences where like an is n, and then n goes to infinity, this thing goes to infinity. So it doesn't have a point, a finite point it kind of converges to, and also if you just put minus, it also goes to minus infinity. So these kind of things where the sequences goes to infinity in a positive and negative sense, we say it diverges. And also, I just told you about like infinity, but there's also a concept where it doesn't converge if, for example, I'll just give you example after the slide, just a minute. Oh, there's no, wait a minute. Oh, there's one, okay. Okay, we'll show that if, for example, the easy one with the proof, which is we already used the concept of sequence where an is 1 over n, we want to show that, for example, rigorously, that as an goes to 0, n goes to infinity, which is very intuitive, but we're going to solve it in a more rigorous term. Okay. And I think it's very important that you guys remember this sort of proving methods, because this sort of proving style will be very used frequently in proving things in analysis and calculus. So it's very like similar, like all of it, like kind of like a variation of this proving method. So just get used to the very simple ones first. So we prove it like this. Okay. So we have to show, remember the definition, which is for every epsilon, there is some n such that the absolute value becomes smaller than epsilon if we take the index large enough, right? So if we find some sort of n for every epsilon. So to start with, we just get some arbitrary epsilon. So let epsilon be given. Then we have to choose some n large enough such that 1 over n minus 0 is smaller than epsilon, right? By the definition. And this, I'm not sure if you remember this, but remember when I did Archimedean property, there was a one when I said like we can actually say that 1 over n is smaller than epsilon. Like, because basically, this is saying, if you reverse it, it's saying we have to find some sort of natural number n that is bigger than 1 over epsilon. And that, remember, that holds by the Archimedean property, because for any sort of real number, positive number, we can always find some natural number large enough that it's going to be bigger than that. So we can find a number that exists. And because that exists, we can just choose n large enough so that this holds. So that the 1 over n is smaller than epsilon. We can always choose n for that epsilon. And since we did it for arbitrary epsilon, the proof ends. This is how we've kind of solved it. And just note that this is also, remember that epsilon is a positive number, it's not a 0. So you can take epsilon as small as you can, but you're not taking epsilon to be 0, because otherwise it's not going to work. That's why we're not saying like n goes to, remember like we said n goes to 1 but not exactly 1. It's kind of, that is like included in this concept. So what we're doing is that kind of way, like for any sort of epsilon, we're squishing the sequences small enough that it goes inside the triple. And this holds because of the Archimedean property that I explained in the former section. Any questions? So I put in the slide. So we remember learning about Archimedean property, and this is why it's important, because it's frequently used in this sort of setup. You'll see a lot of the proof later on where the proof kind of ends like we can get n large enough to do this, and that's like you're using an Archimedean property to say this. You can't say that unless you are assuming Archimedean property. Like you're taking n large enough, and you're taking n small enough, thing like this. It's all sort of Archimedean property concept. So, and you'll see this a lot of these sort of proof like frequently when you're solving things. All right. Some exercises, and I wanted to like highlight number 3 because there are cases where sequence doesn't converge, so it diverges, but it doesn't mean it goes to like positive or negative infinity. So you might already know this number 3 example, but some like an exercise. So what does number 1 tends to or goes to as n goes to infinity? Yeah, 1. It goes to 1. It's very simple, right? It goes to 1. And you can also prove it with the similar way I did, like using the limits. You can try if you later on. So like you can use it as like an exercise. You can try, and they can be all proven. So, oh, just for like reminder, because there are cases like number 2, we're actually showing that this sequence is diverges, right? So there's a point in time where you have to show that some sequences doesn't converge. So that's the way to do it is write it. So remember that the definition of a limit was that can you guys all see it? It might be small. 보이시나요? Oh, and another useful abbreviation. Instead of saying such that, math use a lot of ST. No, it's holds for such that. So for every epsilon, there is, oh, sorry, I did delta. There is n. There is n. And curly n is natural number. So there, for every epsilon, there is some n such that like this holds, and if you want to show that something doesn't converge, you kind of reverse the process. So it always confuses me, but something like, I think, for all n, there exists some epsilon such that correct me if I'm wrong. I think this is the right one. So it's kind of confusing because you're kind of showing something converge, and then if you reverse it to show something doesn't converge, you have to show that for all n, for all natural numbers, so any sort of sequence, you have to show that there is some epsilon now. So it's reversed. Instead of for all epsilon, now there exists some epsilon. And instead of saying there exists some n, now it holds for all n. So all n, there exists some epsilon such that the interval is going to be bigger than the epsilon. So kind of intuitively kind of means is that in the past when you're solving for convergence, you're kind of showing like for any interval n goes inside it. Now what you're kind of showing is that for for any n, there's going to be some sequence that's going to go out of this sequence. That's going to go out of the sequences. I mean interval. So like example would be the question 3, for example. -1 to the power of n. So what this is, you can see that easily that this function, this sequence has like 2 values, which is 1 and -1. It's like, it's gonna go like something like this, right? You can kind of see that this is also not going to converge because this goes to 1, this goes to -1. There's no exact point it's going to go to 1. There's no one limit it's going to go. And if you're proving it in this way, you can kind of see what you're doing would be like, if you do some epsilon interval that is between 1 and -1, you can easily see that any kind of sequence you choose is going to be outside this interval, which means not converging, at least to 0. So we can kind of show that this doesn't converge to 0, and you can also show that this doesn't converge to 1 because even if you have an interval here, you can always choose these points. And they're going to be always points in the future that's going to be outside this interval, which shows that it's not going to converge to 1. This is kind of a way to show that like the sequence doesn't converge to some points. That's how you prove it. So, but it's not that important. But so basically, like the concept you should remember is that basically limits of a sequence or a function later on is going to be mostly about like after some point in the future, after some point n, there will be the sequences or the function will be always be very inside some very small interval. So after some n plus 1, some big numbers, all these values of the sequences, they'll be inside a very small interval, so close that there's no point that's going to go out of it. That's kind of how you remember it. So. Any question? And you can kind of see that the question 2 and 3 are not going to converge. And the second one, as I said, doesn't converge because it goes to infinity. And the third one is an interesting part. It doesn't converge not because it goes to infinity or negative infinity. It's because there's just not a point where it converges, like literally. There's always going to be some deviations. And there are many more other examples of sequences you can try to see how it converges. So you can always use the similar epsilon n method to solve it. And, oh, I already put it here. So exists of a limit. So limit not always exist. That's the very important part you should know. Like, there are many cases where limit doesn't exist, and I said an minus 1. So you can see that, you can clearly see the sequence never converges to some point. It's always 1 or minus 1. I mean, if you define sequence, I mean, if you define a limit to be like, maybe there could be like more than one limit, then maybe it could hold, but usually when you say limit, we say it's a unique one. So in this case, it never converges. But you kind of see that this is a bit problematic because there are only many sequences that are not going to converge. You already see a lot of examples, right? But that's problem because we want to use limits a lot. But if there are a lot of the sequences where limit doesn't hold, it's kind of useless to use this property because there's very much limits, because there are sequences that doesn't have limits that we cannot use the property of a limit. So limit has some problem in the sense that it's a very strong assumption for some sequence to have a limit. So what are we going to do? That is, we're trying to see if is there some way to use limits sort of definition that exists for maybe any kind of sequences. So because limit doesn't exist for all sequences, maybe there are some definition we can use that kind of exists for all sequences. Maybe. So we're trying to find this. Oh, I wrote it here. Oh, and just before we go on to that concept, there's some nice theorem that you should know that kind of makes your life very helpful. You don't need to know exactly how it kind of works, just kind of remember the concept, which is, I think you might already know this, which is monotone convergence theorem, but before we talk about monotone convergence, we have to know what monotone means. So I wrote it here. So what it means is that we say that the sequence of real number, Sn, we say it's monotone increasing or decreasing if that holds. So what you can see is like very easy to understand. So basically it kind of goes up or goes down forever. So like, in a x and y stuff, the value of the sequences will go either from like this, so this is monotonically increasing, or down. And we wouldn't say a sequence is a monotonic if there's like a bump, like if it like goes like this or goes like this. So we were saying like it's monotonic if it keeps on increasing or keeps on decreasing. So that's like proper monotone sequences. So what is MCT? Monotone convergence theorem is that suppose a sequence is monotonic, so either it's monotonically increasing or decreasing, then the sequence converges if and only if it's bounded. So what does this mean? Let me just talk about the concept of bounded. So what does it mean is that it's also very intuitive if you think in graph. So let's say that firstly, let's assume that the sequence, let's just the sequence is monotonically increasing, so it should be like this, right? It should go up some points like this. And what does it mean is bounded is that a sequence, we say a sequence is bounded if there's a point like B where all the sequence values cannot go over this point. So basically there's no point like here for sequences. It's always behind here. Then we say it's bounded if the B is some finite number. Then you can kind of intuitively see that if you assume that the function, sequence, is monotonically increasing, so it's going up, but all the sequences are bounded by this, you can kind of think that it's going to converge, right? Because it's not going to go like up here. It's going to be staying below the bar of B, but it's kind of increasing Well, I mean, it could be like equal, but still, it's like it's monotonically increasing. So there will be some kind of point it's going to converge to in the end. So that's like the intuition of monotone convergence theorem. So what it says is that in the theorem, so if you suppose that the sequence Sn is monotonic, then if the sequence is bounded, it's going to be converging. So that's like a nice thing to show that something converges. Because remember that if you want to show that something converges, you have to use all that complicated epsilon and n concept to show it. But if we use the MCT theorem, we don't need to do that. We just need to show that if sequence is monotone increasing and bounded, we can just say it converges. So instead of using hard concept of epsilon and n, this kind of sometimes makes your life very easy. So just remember this. It's an important concept. And we have, now we go on to more about how we want to define limit sort of concept for every sequence, which is subsequences. So, as I said, the sequence having a limit might be too strong assumption because there are sequences that doesn't have a limit. So, let's consider like subsequences. So what does this mean? And some intuition for doing that is because, for example, remember the -1? Remember this? -1 over n, it has the value of either, let's say this is 0, and this is minus and this is 1. Remember this value always goes like this, right? But think about this. This has no limits, right? But if we just restrict the sequences to just this and this, we have a limit, right? Because if we just think about sequences here, this converges to 1. And for all -1s, they converge to -1. So if we just think about some parts of the sequences, they can converge. So like this, these would be like, you know, A2, A4, A6, A8, A10, right? These sequences are all going to be 1. So if we think about like a subsequence of sequence, we're kind of thinking in a way where they're going to converge in this subsequence, even though in a whole sequence it doesn't converge. So that's where the subsequence comes, and here's like a more rigorous definition, which is, so for sequence an, we're considering a sequence nk of positive integers, such that n1 is bigger than n2, n3, then we call the sequences as subsequences. And if the subsequences converge, we call this limit as subsequential limit. It's a very like difficult definition, but basically this means is that what we are doing is like similar to this. So for any A1, A2, A3, A4, A5, what we can do is we can just make a new subsequence out of it. Like we can just choose this, and this, and this. And this is like a subsequences, right? Or maybe instead of choosing this, we can just start from A3 and then go from A3, A5, A7. So basically what we're doing is just like we're just picking some partial parts of these sequences to make a subsequence. But it's still a sequence because it just keeps on moving forward, right? So those are called subsequences. And if those subsequences have a limit, we call them subsequential limits. So in this case, like -1, that would be like this, right? If you choose only like even numbers, you get a limit 1, right? And we call this limit subsequential limit of this subsequence. Okay. I already wrote it on the slide here. See, like, we can consider subsequence like A2, A4, A6, and we can clearly see that this sequence has a subsequential limit, and hence, we can sort of use limit-ish term by making a weaker assumptions. Because before, -1 over n did not have a limit, but since we define subsequences, it does have a subsequence limit. So even if this doesn't have a limit, we can use the concept of subsequential limit to define some property limit. Although it's different, which is a lot weaker assumption. Okay, this is going to be the confusing part. So, but the problem of subsequential limit is that there are just too many of them. Think about it, like this case. We have 1 and -1, right? But the problem is they do have a limit, but then they have 2 subsequential limits. This is problematic because we're saying like for any sequences there's like more than 1 limits. So there are so many subsequential limits that we're not sure how to define this, how to utilize this, because, and this is just easy for this one because it just has 1 and minus 1. Like for example, like, consider like, consider sequences like this. Like an and n, it goes infinity, right? Because we can choose subsequences, what this does is just goes to infinity, and there's just like numerous limits, and some other sequences where there are going to be many kinds of different categories of limits if you just choose the right subsequences, right? As long as you just do it whatever you want, because there's no limit in taking what subsequences. So there's like problematic parts, because we want to use subsequential limit because it exists for every sequences, it seems. But the problem is they have so many subsequent limits. It's kind of hard to control it and use it. So, because there are so many subsequential limits, what we're going to do is we're going to only consider biggest and small subsequential limits. So that's how we're going to do it. It's kind of way, because there are a lot of subsequential limits, we'll just kind of make a bound so that we're just going to think about biggest one and smallest one and just consider them. So that's where the concept of this weird lim sup and lim im comes up. Oh, sorry. All right. Okay. So let am. So this is a like rigorous definition. Oh, and just information. I didn't explicitly say this, but there's a notation that I'm going to talk about later on, which is sup and inf, which is not a different concept. We already talked about this, but I didn't use the notation. So let me just talk about it as I talk about the definition. So definition of lim sup and lim inf is let an be a sequence and let a be set of all subsequential limits of an. Then we define lim sup an as sup a and lim inf as inf a. So what does this mean? So, and firstly, before we start, let me talk about the definition of sup and inf. They denote supremum and infimum. So do you remember like upper bound we talked about? The upper bound and lower bounds? Like we talked about a set in the past where, you know, like x is smaller than root 2. And we talked about upper bound for this, right? Which was like 2, 3, 4. And there are upper bounds for the set. And we talked about that the least upper bound is root 2, right? And we kind of sort of say this as supremum of A. So it's like another definition we can use. So when you say like sup of A, which is this set, basically means it's the least upper bound. So it was LUB. We can also say this is like sup A, like different notation of least upper bound. And likewise, there's also going to be a case where A is like, instead of being smaller than root 2, there'll be something like, I'm not sure if this is correct, but maybe there's like a backward where we're thinking about all sets that are bigger than root 2, and they're going to be lower bounds, right? Elements that are smaller than root 2. So it's like 0, minus 1, etc. And then out of all these lower bounds, they're going to be the biggest one, which is root 2 here, right? And we call this the greatest lower bound. And this is also denoted as, oh, wait a minute. I think I got it backward. 맞나? 임 맞는 것 같아. Okay. I think it's right. Sorry. We call this inf A. So it's infimum. Oh, just tell me if I'm wrong with the notation because I could be like confused by this. But we just call this like inf A. So infimum and supremum, this is like the word we use. So, and so that's the definition of sup and inf, which is just denoting just the least upper bound and the greatest upper bound. Just remember that. And what this is saying is that, remember that, let's remember the minus 1n case again. So, and think about all the possible subsequential limits you can have for this. And for this one, it's very easy, because you can kind of see that there's only two subsequential limits, which is minus 1 and 1. So this is going to be the A in the definition, which is set of all subsequential limits A is the set of all subsequential limits. Then we've defined lim sup as the biggest of these two, which is in this case is 1, right? And we define lim inf as the smallest of these sets, which is -1. And that's the definition of lim sup and lim inf. And we're kind of using it because in the case that there are a lot of subsequential limits, we can't consider all of these. So what we do is we consider lim sup, the biggest one, and the small subsequential limits. And if we consider only those two, it's a lot better to kind of understand how this process of limits are going. So we're using the lim sup and lim inf definition to kind of make this more easy to understand. But then if you are more if you kind of understand these overall concepts, you might have a you might already encounter some problem, because there are cases where, I mean, what if like subsequent limits all go to infinity? You know, like, and I say like an is n. For this one, every subsequential limit is going to go to infinity, right? It goes just go to infinity. So what does happen? What about these cases? They're not going to have these sort of finite limits, right? Subsequential ones. And this is solved if we just like define. It's like solved by defining them as infinite and infinite, infinite or minus infinite, which means in the case like this, where there is just no subsequential limit that is finite, it goes to like infinity. We just define in this case like lim sup is infinite. And for the other case where the n goes to, for example, if all the subsequential limits go to minus infinity, we just define the lim inf to be minus infinity. So by doing this, we can define lim sup and lim inf for every sort of sequence that we can have. So that's very, very convenient, because with the limit we can't do that. But with lim sup and lim inf property, we can make sure that every sequence has some sort of definition of a limit, sort of ish concept. Okay. So what's the advantage of using lim sup and lim inf? So I already talked about it, but let me just enumerate it. So we already have a limit. Why do we use lim sup and lim inf? Because, well, limit does not always exist, but lim sup and lim inf always does. That's why you use it. And in fact, a sequence Sn has a limit if and only if lim sup and lim inf is equal to each other. So what this kind of shows that just using lim sup and lim inf is a lot easier, because as long as you kind of find what these twos are, and if they're equal and they're finite, you just kind of already show that they have a limit. So like lim sup and lim inf is kind of like a more weaker condition for finding a limit. So you can kind of use it more generally. And also, okay. The third reason is because, as I said, considering the subsequential limit is more weaker assumption than considering sequence limits. And math-related people usually like things to be general as possible. So when they're trying to define something and use some concepts, they want to make the things to be with weaker conditions as possible, make it more abstract. So like lim sup in that way is has more weaker assumptions than limit concept. So that's why we're using them. And oh yeah, and you can kind of see that the part where I said like lim sup and lim inf is same, that means they have a limit. For example, like sequence for n1 over n, you can kind of see that if you get all the subsequential limits, it's going to be 0, right? There's only 1 point. So in this case, lim sup and lim inf is same. So this means there's a limit. So it's like a weaker condition. So they can be same elements. Okay. This is just few sequences that is quite useful if you know them. You might already know them, so I just wrote it down. And for more proofing methods, you can also check the Rudin's textbook. So as it is in the slide, which is as long as p is a positive value, the 1 over n, 1 over n to the power p is going to be 0. It's very intuitive, right? It goes to 0. It's like those 1 over n quality sequences, as n goes big enough, they all go to 0. And similarly, if p is positive, well, p over, I don't know how to say this, but p over 1 over n, it also goes to 1 as n goes to infinity. And also about how some properties of p is positive, and there's some alpha that is a real number. then that weird looking sequence also goes to 0. Which is actually like you use number 3 to solve number 4. Number 3 is a more general case. So you might be more familiar with number 4, which is if as long as the absolute value of x is smaller than 1, xn's limit goes to 0, right? If you think about it, as long as you have some sort of 1 over 2 or 1 over 3, you keep on multiplying them and they go closer to 0, right? Like those are very useful sequences you might have to use. So it's very important to know these special sequences. So, and also like number 3 is like kind of like, it's also very intuitive in the sense that it kind of shows that actually power function, I'm not sure it's power function, it kind of shows that the power function is smaller than, it becomes small, like exponential function becomes bigger, faster than the power function, which means like you can kind of see like, you can see the denominator, which is so what that kind of shows intuitively is that you have this, right? And this goes to 0 as n goes to infinity, which kind of means that this part becomes bigger more faster than this part. Because if this part becomes more bigger, it's not going to go to 0, right? This part goes to 0 more faster. And this is intuitive in the sense that if you remember, like, this is like an xn sort of function, exponential function. And this is something like, what would you call like xn n squared, something like this? Oh, yeah, like x squared. No. That's kind of hard to say. Oh no, it's like exponential function, sorry. So like, it's like comparing like this sort of function and this sort of function. If you remember, x squared goes like this, right? And like this. And 2x squared, although it starts in a similar way, start from 1, it becomes strictly more bigger as 2x goes bigger. So what this kind of means is that as the value goes to as value x goes bigger, x squared becomes 2x squared becomes a lot more bigger in a very faster way. So you might already know this, but it kind of shows that this function becomes more faster, which is the reason kind of shows intuitively that the exponential function becomes bigger, more faster than the normal, what we call the, I'm not sure how to call it, polynomial function. All right, so polynomial function is basically smaller than the exponential function in growth. 교수님 왜 전화하시지? Okay, so we have a series, but due to the time limit, I think we'll end the section here, and this is going to be end of the session 4. Well, thank you for listening to the course, and we'll see you tomorrow.